Okay. All right, so we've been talking about forces and what we've done with forces so far is we've converted, well, first we talked about Newton Euler force torques. And then we converted these to what we call the Lagrange force. Okay, and then we saw how these things came up in the equations of motion. Okay, and so sort of three equivalent versions of the equations of motion, one of which is some sort of abstract version of what you learned with force moment balance in your physics courses. Okay. So in the process of doing all of this discussion, we were kind of doing something a little bit silly. Forces were assumed to now just to be just functions of time. Okay, and that's not wrong necessarily, because certainly what's true is that at every time the forces will assume some value, but typically forces come to you not as functions of time, but as functions of time, position, and velocity. Okay, so we'll talk about specific cases of those kinds of forces, all right? But first, let's sort of say in general how you would define a force, okay? And the most convenient representation in which to do that is the geometric representation, okay? So, the definition doesn't need to depend on mechanics really at all. It's a purely geometric definition, which has mechanical sense. So we're just going to let Q be a manifold. Possibly the configuration manifold of an interconnected mechanical system, but doesn't have to be. So a force on Q is a mapping. So I'll call it capital F, as we've been calling the Lagrange force. And it's going to depend on time, which is a variable in the real line, and position and velocity. Okay. And it will take values in the cotangent bundle. Okay. And of course, it has to have some properties. And really, there's only one property here. And that is that if you apply a force at a time and position velocity, because that's what a point in TQ is, right? It's a position and a velocity. Then it's going to assign to that a cotangent vector, and the cotangent vector, of course, should be at the same position as the velocity was. Okay, so expressing that mathematically, it says that F at time. Okay, then we're going to take a point in TQ, and a point in TQ is a tangent vector at VQ, which we write like that. Sorry, a tangent vector at Q, which we write like that. And the requirement is that this be in the cotangent space at Q. Okay, so this is like vector fields and covector fields in some sense. It's just the argument now is a little bit more general, but the idea is that things happening at Q should happen at Q. The force you apply as a function at a configuration Q should be a force at the configuration Q. All right, so that's what a force is. Okay, now, so given a general force like this, Okay. And now let's just also take a Riemannian metric on Q. And again, the Riemannian metric need not be the kinetic energy metric for an interconnected mechanical system. And that's kind of the whole power of all the stuff that we've been learning, is you can lift its abstraction up away from physics and get away from all the distraction of the specific physics and talk about general structure. Okay, so given a general force F, just like I defined, on Q, and a Riemannian metric on Q, so a Riemannian metric G, of course. Okay, we have the forced geodesic equations that we've been talking about, but now again, sort of removed from the requirements of being just in a mechanical context. Okay, and they're just the same equations that we have been looking at. You have the part of the equations, which is the geodesic equations for the Levi-Civita affine connection. Then you have the force, which is evaluated at a time, and then a position and velocity. So that, of course, that's going to be gamma prime. That's the velocity. And then we're still going to have this G sharp here. Okay. All right. So again, this makes sense without any assumptions about there being mechanics or physics or anything underlying that. It's just a purely mathematical thing. Okay. All right. Okay, so types of forces. All right. So forces depend on t, time, and position and velocity. All right, so we're going to consider maybe omitting various of those kinds of arguments. Okay, so a very common kind of force is time independent. Okay, so a time independent force doesn't depend on time. Okay, so how do you say that? There exists a mapping F naught from, okay, and so basically I'm going to, I'm going to have the same kind of thing as a general force, except it's going to omit time as an argument. Okay, so it's just going to be a map from TQ to T star Q, such that F of T VQ equals F0 of VQ. Right, so that's just sort of elaborately saying that F doesn't depend on time. Right. What's called a basic force. Okay. All right, so I'll give you the definition. And so a basic force is a time independent force that also doesn't depend on velocity. Okay. And so, phrasing things like we did in the time independent case, that means we're going to have a force like F, but the dependence of F is going to eliminate R, and it's going to eliminate T in the TQ part. So it's just going to be a function from Q to T star Q. Okay, so there exists, I'll still call it F naught, but in this case, it's going to be a mapping from T to T star Q, such that, again, F of T VQ equals F not of Q. Okay. So again, it's just expressing precisely what you mean to be independent of time and velocity. Okay, but this is something we already know. What kind of a geometric object is this? So it's going to be a mapping from Q to T star Q, and it should have the property that at every Q, it takes values in the cotangent space at Q. We had a name for those things. A covector field, right? So it's just a covector field. That's all there is to it. Okay, so we call these things basic. So basic forces are just covector fields. And the reason you call them basic, and so let me write this down and I'll tell you. Okay, the reason that you call them basic is that you have, so there's a common thing that you do in these kinds of constructions. You have R cross TQ, okay, all right, and then we have a force F here, right, and it takes values in T star Q, okay. Then we have a mapping like so, which just projects us into TQ, okay, so this just takes a T and a VQ and it just gives you VQ, and then we have an additional projection, Q, okay, from which takes a V sub Q, sorry, takes a V sub Q and just returns Q, okay, so that's the projection here, okay. And a general force maps you from here into here, okay. But a time-independent force looks like this, okay, and then a basic force looks like that, okay. All right, and they call it basic because Q is what's known as the base space for TQ. Okay, so TQ has a projection down to Q, and the terminology is that you call Q the base space for TQ. Okay, and again, this makes reference to some general stuff that we're not talking about. But anyway, just wanted to explain to you where the term basic comes from. Okay, it doesn't mean basic in the sense of, you know, simple or elementary, or means with respect to the word base space. Okay. All right, so there's a simple example of a basic force, and that's a potential force. Okay, so a potential force is a basic force where the covector field, F naught, has a very specific form, namely it's the differential of a function. Okay, so there exists a function V called the potential function. Okay, such that F is the basic force. Okay, so it's one of these guys. Okay. With F naught equals minus dV. Okay, so in other words, F, a potential force, depends on time and position and velocity, but it doesn't depend on all that stuff. It only depends on Q, and moreover, it depends on Q in this very simple way. Okay, that's a potential force. Okay, so potential forces have associated with them, and we'll talk about this, a potential energy. Okay, so that's where potential forces come from. And so typical examples of potential forces that you are very well familiar with are spring forces are potential forces. Okay, because I'm just talking about a normal standard spring, no fancy hysteresis or anything in it, just a spring. And the force that a spring exerts is proportional to the amount that the spring is stretched. For a linear spring, and you can have non-linear springs, but the point is that the kinds of spring forces I'm talking about depend only on the relative positions of the endpoints of the spring, right? So it's, the distance from here to here determines what the spring force is, right? And if you increase the distance, the spring force increases, and if you decrease it, the spring force decreases. So that's a force that depends only on position. Okay, a gravitational force. Okay, so gravitational force is a potential force. And so the spring force has a potential V is 1/2 some constant, the spring, in the case of a linear spring, it's a constant K times the deflection of the spring, which I'll call delta squared, right? That's the spring potential energy. And the force exerted by the spring is dV. Okay, and so given your mechanical system, that term delta squared has to be calculated in terms of the coordinates. Okay, so that's something you have to calculate, but that's the potential energy of a spring, a linear spring. Okay, the gravitational force is, of course, V is m acceleration due to gravity, which I'll write as a sub g, h, where h is the distance or height, I should say, above or below, if it's negative, some reference plane. Orthogonal to the direction of gravity. Okay, so gravity has a direction associated with it. And what you typically do in practice is you choose your spatial frame in such a way that gravity is aligned along one of the spatial axes, just to make your life simple. And then h in that case, so let me maybe sort of flesh this out a little bit here. Okay, so if gravity is a Newtonian force, okay, so it's a vector in R3 acting in some direction here. So m a g, and this is going to be a vector now. I'm just going to call this vector v. Okay, so this is going to be the direction of gravity. Okay, and then there's going to be some plane, okay, which is orthogonal to v. Okay, and then you're going to have, say, so I should be careful here. It's the height of the center of mass. Okay, physically. Okay, so I have some body here floating around, and its center of mass is, let's say, located there. Okay, and then I have a distance here, which is h. Okay, so again, you know how to do this in practice, but to sort of do that in some kind of generality, that's what it looks like. Okay, all right. So so potential forces are particularly interesting. So let's talk about potential forces for a little bit. Okay. So why are potential forces interesting? Well, I think a good characterization of potential forces comes in terms of work, okay? And a potential force is a force which does no work around any closed curve. So a force, so let me say a basic force, just to simplify to the case that is pertinent. Basic force F0 is a potential force if and only if the work done by F0 along any closed curve okay, and a closed curve, of course, means one that stops where it starts. Okay, so i.e. a curve gamma, and without loss of generality. Well, let me just do it generally for a second. Okay, so a curve gamma defined on some closed interval AB with gamma of A equals gamma of B. Okay, so it's a loop. Okay, so the work done by F naught along any closed curve is 0. Okay. So I don't know, maybe this, I don't know, and I think it probably depends on who's teaching the course, but this may have shown up in your vector calculus course. It also probably showed up in your complex variables course in terms of integrating around closed loops, that quantity being 0. But let's look at that in a mechanical context. Okay. So an example. Okay, so I'm going to take our stupid robot example and consider a stupid version of it. There. Okay, just a robot with a single link. All right, just for simplicity. Let's use a force on this thing. Okay, so we go through and we do the modeling for this, and we determine that there's an angle here theta, which is a coordinate. Okay, so so Q is of course S1. So we talked about that on the very first day. Okay, and it has a coordinate theta. Okay, now let's consider the force. So consider the basic force F equals d theta. Okay, and so this is a basic force because the component, the coefficient of that force is 1, and in particular 1 is independent of time and velocity. And it's also independent of theta, but for it to be a basic force, it only needs to be independent of time and velocity. Okay, so that's a basic force. So the question, all right, and so this just corresponds physically to applying a torque to this thing of some constant magnitude, and the magnitude I'm assuming is 1 in some appropriate set of units. Okay, is F a potential force? Okay. Well, I mean, obviously it is, because it's the differential, right? A potential force is one which is the differential of a function. And, I've written it like it's the differential of a function. So obviously the answer is yes. Okay, but of course the answer is no. Right? So let's see why, and let's explain also, let's also at the same time see why this thing really, although it looks like it is, it's really not the differential of the function. Okay, so let's, to verify that this is not a potential force, let's just take a look at that characterization. Okay, so let's take a closed curve. T goes to, so it's a curve in S1, and I'm going to write a point in S1 as x comma y with x squared plus y squared equals 1. Okay. Like so. Okay, so this is a closed curve defined for t in 0, 1. Okay, so this is the curve which just goes around the circle once. Okay. Okay, so it starts here, goes around, and ends here. Okay, so that's my curve. So let's calculate the work done by the force F along this curve. Okay, and so let's call this curve gamma. Okay, so in coordinates, okay, gamma prime. So actually, first let me write the curve in coordinates. So in coordinates, gamma has the local representative. T goes to T. Okay, so this is so expressing theta as a function of T. Okay, so theta of T is equal to T, right? I mean, that's right, that's theta right there. All right. Okay, so then what I want to do is I want to calculate the work done by F along the curve gamma. And so work done, so work is the integral from 0 to 1, right? That's over time, okay? So it's going to be F at gamma of T acting on the tangent vector gamma prime of T dt, right? That's the general definition for the work done by a force along a curve. Okay, so now we're just going to plug in everything for the specific F and the specific gamma that we have, okay? So this is the integral from 0 to 1. Okay, so F is d theta. Okay, and then, okay, so if the curve gamma is given in the coordinates theta by just t, then gamma prime is equal to just 1 times d by d theta. Okay, so it's d by d theta dt. Okay, so this is F, and this is gamma prime. Okay. All right, so the definition of the various symbols involved, the d by d theta and the d theta, means that that thing is 1. Okay, which is not equal to 0, of course. All right, so that is enough to show that it's not a potential force because I have a closed curve and the function does work around this closed curve. Okay, so then, we sort of have kind of two contradictory answers here because our definition of F says that it's the differential of theta. Okay, but our characterization in terms of work says that the work done along a closed curve is non-zero. which answer is correct and why? Well, the closed curve answer is correct. So why is the F is equal to the differential of the function theta? Why does that not make F a potential force? So theta, if you're going to take the differential of a function, the function should at least be differentiable, right? And normally in this course, we're always working with things that are infinitely differentiable. Okay, so is theta an infinitely differentiable or even differentiable function on S1? Is theta even a continuous function on S1? Okay, so what's the value of theta? Well, the value of theta here is 0. Okay, but then the value of theta here is 2 pi, right? So theta is actually not even a continuous function. And so, this is the coordinate representation in the coordinates of F. Okay, so F is perfectly well defined. Okay, so F just kind of points in the theta direction, right? So there's nothing wrong with F being equal to d theta. So in other words, F is 1. F kind of looks like this. Right? And so when you get back here, it agrees with itself, right? So there's no contradiction with d theta being an infinitely differentiable covector field on S1, but in fact, theta itself is not an infinitely differentiable function. Okay, so the contradiction here between F not being a potential force and F equals d theta. Okay, so in other words, looking exactly like a potential force, is that theta is not a smooth or even continuous function on S1. Okay. And so this illustrates, a point, and the point is you have to be careful sometimes when using coordinates. And so a typical situation where you have to be careful is exactly things which involve rotations like this. Okay, and you need to be careful that the things you talk about actually make sense on S1, or if they don't make sense on S1, that you're honest about that. Okay, so for example, you might want to do something where you work with the function theta squared. Right, that's definitely not a function on S1. Sine theta is okay, right? So if you take the function theta, which is not continuous, but you take the function sine theta, right? That's going to now be a perfectly well-defined function on S1 because sine kind of gets rid of the, because sine is periodic, it gets rid of the discontinuities involved with the function theta, which is not periodic. Okay, and so similarly, cosine theta is fine, but theta squared is not good. Theta is not good. Absolute value of theta is not good. Okay, so this sort of points to the fact that when you're working with coordinates, especially in the presence of angles, okay, you have to be careful about things like continuity. Okay, good. All right, other kinds of forces. All right, so this was a little digression about potential forces. Let me continue with my list here. Dissipative forces. Okay. And so I'm going to talk about a special kind of dissipative force. I'm going to talk about a viscous friction dissipative force. Okay, so viscous dissipative force is one depending linearly on velocity. It's more than that, but the thing that makes it viscous is the linear dependence on velocity. Okay, so that's something you know about, right? So you know about viscous friction, which is, kind of between a surface and another surface with, some kind of lubrication between them. Okay, so typically the force that that is exerted on a body as it sort of moves over another body subject to viscous friction is a constant times the velocity. Okay, so that's the kind of thing that I'm talking about here. But how do you do that in our geometric setup? Okay, so geometrically, oops. This is modeled by a positive, semi-definite bilinear mapping R of Q on each tangent space. Okay, so it's a bilinear mapping. And so it's positive definite, so it's symmetric. So I'm going to write it in sigma 2 of T Q Q. Okay, so it's symmetric and positive. So whenever somebody says positive definite or positive semi-definite, symmetry is always implied, but I'll write it here just for completeness. Okay. Okay. And the force is F of T VQ equals minus R flat of VQ. Okay, so we saw how you define associated with every bilinear mapping, this flat map. Okay, and in coordinates, it just amounts to multiplication by the matrix associated with the bilinear mapping. Okay, and so it looks like that. Okay, and the reason that that's R is this is typically called Rayleigh dissipation force. Okay. All right, good. All right, so now, so those are the kinds of forces that I'll define. Okay, we're not going to talk, we talked a little bit about potential forces. I'm going to show you why dissipative forces are called dissipative forces. Okay, and the reason that they're called dissipative forces is because they dissipate energy. So that requires us to talk about energy. So we have kinetic energy. And we've introduced potential forces, which have a potential function, and that energy is typically called potential energy. And so you can combine those two things to get the total energy, and we'll sort of drive some things which kind of indicate how why that's maybe a reasonable thing to combine and call the energy. Okay. All right. So we have kinetic energy. KE. Okay, if we have a potential force minus dV, that's what a potential force looks like. Okay, so we're going to call V the potential energy. And the total energy is just going to be the sum of those. Okay, so you know, we should be careful here. We're restricting energy to be a very specific sort of energy. Okay, kinetic and potential. There may be other, in a given problem, there may be other important things to think about, but for this discussion, it's kinetic and potential. So the total energy is E of VQ is kinetic energy, so 1/2 G of VQ plus V of Q. All right. Okay, so there's a couple of things that are interesting to do here. Okay, and I have 10 minutes. I won't rush through this calculation, so if I don't finish it, I'll do it properly next time. Okay, so let's calculate, because I want to do this right. The time derivative of energy, okay, with an additional non-potential force. So I'm not going to include the force that comes from this in the potential function, so it's a non-potential force. F. Okay. All right. So I just write down the energy and then differentiate. Okay. So d by dt of the energy at gamma prime of t, okay, is d by dt of, so the energy is 1/2 g of gamma prime of t plus v of gamma of t. Okay, so that's the energy. Okay, so now I just differentiate. All right, so now I'm going to differentiate this term first, and this is kind of a triple product going on here, right? I have three things that appear kind of multiplied together. I have g, I have gamma prime, and I have another gamma prime appearing in a different argument. Okay, so when I differentiate this, I'm going to get three terms. Okay, one corresponding to differentiating in sequence each of those while holding all the other ones fixed. Okay, so let me do that. So I'm going to write down a symbol which won't necessarily make sense, but that's okay, because it's going to be 0. Okay, so I'm going to differentiate first g, okay? And the derivative of g, I'm going to write it using this symbol here. So, and then I'm going to explain to you why that's 0. We've already seen why that's 0. Okay, then I'm going to hold g fixed, and I'm going to differentiate first this, holding that one fixed, and then this, holding that one fixed. Okay, but g is symmetric, so those amount to the same thing. So basically, there's going to be the same thing with a 2, and the 2 is going to cancel the half. So I'm going to get g of nabla g gamma prime of t, gamma prime of t, gamma prime of t. Okay, so that's the derivative of the first term. Okay, now this term is equal to 0, and that's because of one of the defining properties of the Levi-Civita connection. Okay, if you look back at our definition of the Levi-Civita connection, you will see there's two properties. One is, involves the difference of the covariant derivatives of x and y is equal to the Lie bracket. And then there's this other term. And if you apply that other term in this case, you see that what that means is that this is equal to 0. Okay. So good that I don't have to define what that symbol means because it's 0. All right, good. So that's the derivative of the first term. Then I have the second term. All right, so the second term I'm going to differentiate by the chain rule, right? Because this is a composition of V with gamma. So it's going to be dV at gamma of t, which is a cotangent vector, acting on the tangent vector gamma prime of t, like that. Okay. All right. Now what I'm going to do is I'm going to stick in the equations of motion, right? Because that term appears in the equations of motion, and in the forced Euler-Lagrange equations, which I wrote up here somewhere here. Okay, so I'm going to write in F. Okay, but F is now going to have a potential term, okay, and then the non-potential term. So I have to include both of those. Right, so this is G, okay, and then I'm going to, like I said, substitute in the right-hand side of the forced geodesic equations. So it's going to be F at T, gamma prime of T, right, minus, so I have the potential force I have to include there. And what's the potential force? Oh, so sorry, I forgot the G sharp there. G sharp F at T gamma prime of T, right? Then there's the potential force, which is minus G sharp of dV at gamma of T, okay? And so the point is this whole business here is just nabla G gamma prime by the equations of motion. Okay, then I have this term which goes along. Okay, good. Now let's look a little bit more carefully at this. Okay, so I have a G here and I have a G sharp here. Well, G sharp involves the inverse of G, right? So when I think about calculating this, this is going to cancel with this, and I'm essentially going to get this cotangent vector acting on that tangent vector. Okay, so it's going to be then F of T gamma prime of T minus dV at gamma of T gamma prime of T. Okay, and so notice the semicolon here means cotangent vector acting on tangent vector. Okay, and I apologize, I didn't do that here, and I should have. Okay. Plus, again, which, and this term is going to cancel with one of the terms in the previous line. And you get this. Is it okay? Does it make sense? Okay. All right. Okay, so so that is the derivative of so I forget, was it the red one you don't see or the blue one? I think it's the red one you don't see. Am I right? Okay, so that is the time derivative of energy. Okay. All right, so there, I've calculated it somewhat carefully, and we'll talk about it next time.